Okay, let's start. So just want a quick announcement that my office hours today will go till noon. Sorry, on Monday I had to unexpectedly cut my office hours short by half an hour. So I'll make up for it today. Just to give you a bit of a preview of where we're going, right? So we have I believe two more weeks of lectures before RRR week. Is it two? I think 2 more weeks of lectures before RRR week. So what I want to do is to achieve two things. First, we're going to spend most of the next 2 weeks talking about generative models and generative AI. Then, in doing that, I want to make sure that we get a substantial treatment of both the modern diffusion models, and I would like to make sure you can understand the road that was taken to get to ChatGPT. Okay, this is my objective. So some of our choices of what we're going to do are going to be aiming at getting you there, but in a way that lets you understand not just these two cool things that have happened basically in the last year in terms of popularization, but also to understand the next 20 things that are going to happen in the coming years. So that's kind of driving a bit of my choices of how I'm going to talk about things. So this part, we're going to finish up our treatment of the basics of fine-tuning. And there's a couple of important things I want to make sure you understand. So this will be a little bit in the interest of speed, right? Everything here is done in the interest of speed. It might seem a little bit disconnected at parts. Ask questions, right? If you have any questions, I do want to make sure everyone understands what's going on. So, first thing I want to talk about is catastrophic forgetting as a phenomenon. I mentioned it before, but I want to make sure everyone gets it. And that will lead us naturally into this topic of knowledge distillation. So this basically refers to when a model learns something new, the phenomena here, it can forget something it already knew. Okay? So from an engineering point of view, this is something that we tend to think of as being bad. Note, there are contexts in which this might be viewed as a feature and not a bug. Okay? But right now we're going to treat it from the perspective of it being a bug, something wrong. So when we have a model, right, that's built in the following way, some pre-trained model, on top of which we add something that's task-specific, and then we get the task performed. If we do this, we talk about catastrophic forgetting. The context is usually that you want the model to be able to do many things. So the most basic case of this actually dates even back before the kinds of stuff we're talking about. It goes like this. You have a model. You're training a model for a specific supervised task. Okay? You want a model to recognize digits. And what you do is you train it with your data in the following order. You put all your ones at the beginning, then your twos, then your threes, then your fours, then your fives, and so on. Everyone understand the kind of kooky training setup we just did? Okay. And you find that after you see a bunch of ones, your training loss and your held out loss on ones is great. Okay? Then you start seeing twos. And When you start seeing 2s, your training and validation loss on 2s gets really good, but your training and validation loss on the 1s gets worse. Everyone see that? You can all imagine that, of course, it's silly to train this way. Hopefully everyone understands it's silly to train this way. And it's completely natural that if you train this way, you won't do very well on the 1s or 2s. Everyone see that? This is like the most basic form of it, right? Is that you want to, so you can think of multi-class classification, for example, as being many different tasks, many different binary tasks. Is it a this, is it a this, is it a this, and so on. So you can imagine how if you train them one at a time, it would be bad. Okay, any questions on that part? So this is what I mean by learn something new, it forgets something it already knew. But when we start thinking about pre-trained models that we're going to use for many different tasks, the same kind of thing can happen, except it won't seem as silly. Okay? So imagine you have a model, and you train something specific for one task. Then you take a different task, and you train for that. Now, if you change this at all, if this changed at all while working on a specific task, then forgetting is a risk. If you don't change this, of course you can't forget, because you didn't learn anything new. Everyone cool with that? So there's many ways that you can leave this frozen, right? You can leave this frozen. We talked about them. You can leave this frozen by only training a task-specific head, like linear probing strategy. In which case, you're not going to forget anything, because your task-specific head is only for that one task. You can also, in the context of language models or anything that can be prompted, you don't have to put the task-specific thing up here. You could put the task-specific thing down here with a soft prompt, right? Again, you're not changing this part, so you're not going to forget. Everyone cool with that? OK. Last time we talked about how you might, instead of changing this by actually adjusting the weights, you might add an adapter to it of some kind, like a low-rank thing that you train only the low-rank adapter. OK? Remember we talked about that at the end last time, where you said you can just adjust the weights by adding a different thing that's task-specific. Again, as long as this thing didn't change, you could use different adapters and different heads and different prof prompts, and there'll be no forgetting problem. Everyone's good with that? But if you were going to do full fine-tuning, then this is a risk. This risk of forgetting. OK. So now we need to understand, like, what it is that we could do about it, and why it's happening. Two things, OK? So first, let's talk about what you can do about it. Okay. So you want to do something to avoid forgetting. So one strategy is I'll call this the gold standard classic strategy. Okay? The gold standard classic strategy is to say, think about the case of arranging your training data with all of your 1s at the beginning, and then the 2s, and then the 3s, and then the 4s. Okay? That was silly, right? What should you have done? Anyone? You should have shuffled them, right? You should have seen all the different classes all the time, right? So what's the counterpart strategy here? to avoid forgetting? Yeah. Yeah. So you want to basically see all the tasks during training. Okay? So this is called, sometimes called replay. But basically it's shuffle in old tasks during training. So what does that mean practically? It means that if you're fine-tuning this part, you have something that's task-specific, task 27, okay? You also have task 1, and so on, all these other tasks that are all feeding off this model. So it says that when you're training for this new task, make sure that you, during training, inject some data that is on these other tasks as well. So that this thing isn't just feeling gradients from this one task. It's feeling them from everything. So if this task tries to start pulling this model in a way that would make this thing forget, the updates coming from those tasks will try to pull it back in a way that's good. Is that clear to everybody? Yeah.
In this diagram, are all these tasks sharing the same exact model, or are they copies of the same original model?
Great question. So if you used, the question was, when you have many tasks and you want to use the same pre-trained model for those many tasks, in the diagram I drew, where you're going to shuffle in old tasks during training, so this is like fine-tuning training, right? Are these pre-trained models shared across the tasks, or are they separate? So if they were separate, then there would be no issue of forgetting, because the old task, nothing has happened to it. Nothing's happened to its model. So this issue arises only when it is shared. So when it's shared, then you need to, this replay, shuffling in old tasks during training is important as one strategy to prevent the forgetting. So here, what you're willing to do is to say, look, it might be that there are fundamental tensions between these different tasks. Okay, that might be the case. It might be the case that really, when it comes to the capacity of this model, it can't actually support all the tasks. In that case, we're going to have to give something up. Right? There's no doubt about that. Well, in that case, we'll give something up. But in many cases, we expect there's not a problem of capacity of the model. It is actually possible to do all these tasks, because there's natural synergy between them in terms of what the pre-trained model needs to do. We just don't want to forget for dumb reasons, right, during training. And this is a way to stop it from happening. OK? So is this approach clear to everybody? So the important thing to think about when you're doing this is that when we talked about the training data example of just starting a model from random initialization, you want to train a model, you have ones, twos, and so on, then the not shuffling felt ridiculous. Right? Like we should have just shuffled. There's no problem. But when we start using things like words like old tasks, right, and new, okay, we tend to implicitly be thinking that we're doing things in some sequential manner. So we find ourselves encountering a situation. Okay, so this is a big problem when it comes to thinking about models in the context of actual deployment in the world. Because one of the things that happens in the actual world is that things change from when you train your model. And so adding what's called continual learning to models, where they are adapting to what's happening in the world, is actually pretty important for robustness in the real world. Okay, does everyone understand that? Like, it's not like you can just use one thing, because things are going to change. So there is the context of new really means across time. So you might also have a new demand, some new thing you need to do. The big challenge here, core challenge, is data. Right? You need access to old data. Is everyone clear? Right? How are you going to shuffle in the old task during training if you don't have any training data for it? Okay? You also, of course, need access to these task heads, or whatever it is that does the task. If you don't even know what the other task is, then it's harder to imagine being able to defend against it, defend against forgetting it. Do you see that? Okay. So, as an aside, and this is important when we think about the road to ChatGPT. Okay. Aside. What if we don't have access to task-specific data or heads for, quote, old tasks during fine-tuning for our new task. So make it data and heads first. Okay? Does everyone understand the question? The question is, you have a model. You're going to want to fine-tune it for your task. You have task data for your task. You don't even have the data or any task-specific heads for the other tasks. Okay? What can you do to combat catastrophic forgetting? Based on the things that you've learned, the spirit of things we've learned. Does everyone understand the question? Make sure. Raise your hand if you understand the question. Okay, good. So now, what can you do? Yeah?
Data augmentation.
Okay, so I could try to do some data augmentation. So what do you mean by doing data augmentation in this case? What data are you assuming?
Like introducing some data to provide some diversity of the data.
Okay, good. That's a good question. It's a good approach. The approach was saying maybe we can do some augmentation to have some more data that's not just our task-specific data. Am I getting the spirit of what you're saying? Okay, good, right? Obviously, you have to do something, right? Now, if you don't have task-specific data for the other tasks, maybe you can get some other kind of data, right? So this is where you take the approach that we told before about how you think about pre-training, right? Pre-training is designed, we introduce pre-training as, look, you have a bunch of data that isn't task-specific to any task, but it kind of represents the kind of data that you might see. So you can just create a self-supervised task, when we talk about pre-training, to train your model on this massive gobs of data. This data is data, but there's no real task. There's just a proxy task that you make up. So you can follow the same strategy here, right? Which is, shuffle in pre-training tasks. So for example, if you're fine-tuning a GPT-style model for a particular goal that you're trying to achieve, then also mix in some simple next token prediction on gobs of data that's available, the kind of data you had for pre-training. Mix that into. Okay, does everyone see what we're saying? This is, you do this to make it, to say that, look, hey, maybe I don't have stuff for task-specific, I don't have the task-specific data for other tasks you might have used, or the task heads I had for the other tasks, but at least I can use a pre-training thing as a proxy for all the tasks I haven't seen. Got it? So the idea here is the pre-training model of thinking about self-supervision, of having a proxy or a surrogate task, is that this stands in for all the stuff you don't even know you want to do. So you can follow that same strategy to avoid, to some degree, of avoiding forgetting. I mean, it's not as good as if you had the old tasks and their data and their thing, but it's better than nothing. Okay? So, for example, when you look at how the training happens for models like ChatGPT, right, where you had a GPT model that was originally just doing next token prediction, and you want to make it better for the task of interacting with people. During that fine-tuning process, they mixed in pre-training data to make sure it didn't get bad at doing next token prediction. Yeah?
Is there any concept of like changing the learning rate or something so like the newer tasks are like not learned, so you don't learn as much but you don't forget as much or something like that?
Great question. So the question is, while doing this kind of fine-tuning and trying to avoid catastrophic forgetting, do you need to be worried about the learning rates to make sure you don't, does learning rate have an effect? The answer is yes, people have played around with this, of adjusting the learning rates. So remember, whenever you see anyone using, so how do you shuffle in a pre-train another task, right? You have another task. So this other task, you can think of it as adding it to your loss function. Right? At the end of the day, your loss function is a sum over all the tasks, and the gradients come back. Now, sometimes some of those losses say, I have nothing to say, because this is not relevant to, like, I'm not even activated. Whenever you have a sum, remember, whenever you have a sum, you in effect have to make sure the things you add are in comparable units. Right? Does everyone see that? You add two things together, they have to have comparable units. Which means, in practice, you have to put weights on them. Something that gets the unit compatibility correct. When you adjust those weights, in effect, you are also adjusting the relative learning rates for the different tasks. Everyone see the connection? Because if you multiply a loss by something, that's going to change the gradient size, which, remember, gradient size gets hit by the learning rate, so the two things are multiplying. Everyone see that? So in a way, any hyperparameter search on the amount of mixing that you're going to do between losses is also effectively doing a learning rate adaptation. Okay? So people haven't spent a lot of time worrying about separately tuning the learning rate, because it's very hard to disentangle those two things. Okay? Good. But people do think about shaping the loss, thinking about exactly which kind of loss to use. And I'm not going to go into that level of detail. When you read the papers, you'll see them talking about, I'll change my loss from cross entropy to this other. If you study information theory or things like this, you'll learn about how there are variants of entropy that don't use logs, but use raising things to powers instead. So there's variations of cross entropy that are basically based on raising things to powers. They're called Renyi entropies and Renyi cross entropies. So you can think about whether you want to use those, and those are in part meant to shape things about the loss. That's all the next level of detail. I'm not going to talk about it here. Okay, good. So now we've talked about this case of what do you do if you don't have access. You can do the shuffle in pre-training, which is very important. But what if you did have something? So suppose, so now I want to get to the thing that I'll just briefly talk about, and I'll erase it. What if we had a task-specific head but no task-specific data? Okay? So the idea here is you have a model that you're fine-tuning. Let's think of it in two cases. There's task A. Task A head. And then we have the task B head. Example. We only have task B specific data. Label data. So the important thing is that these are YIs. These are task B labels. And this is coming from task B distribution. Does everyone understand the problem? Okay. Problem is we want to avoid catastrophic forgetting on task A. We don't want to forget how to do task A. We don't have task A specific training data. Namely, we do not have task A specific XY pairs. Everything's good? Does everyone understand what we're doing? So yeah, question?
It's a bit hard to visualize when
When might this happen?
Yeah.
Okay, so I'll tell you how this might happen. So the standard example that one might use is like privacy type thing. So someone trained a model, you're hosting it, you're serving this to people, and so you have the task A head, but they use their training data to do the training, so you don't have it. Okay? Now you have a new customer who comes to you with has their training data, and they want to train task B. Okay, so now you want to have task B get adjusted. So if you were just going to do straight fine-tuning, you'd say, okay, now, so one choice you might have, one thing you might think of is, if you're going to serve the second customer, why are you going to start with this block that has already seen task A data? Right? That's a natural question to have. It's like, why not just start fresh? You could just start fresh and serve their own model. But maybe your context is such that you think, hey, maybe there's actually some underlying commonalities between task A and task B. And that's a lot of data this thing was able to feed on. Okay, so this is like this perspective of, you might have heard people talk about it, of machine learning models as creatures that are hungry and like to eat data. And they get stronger by eating data. Okay? So you think, this thing is already fed on task A data. Why would you want to not take advantage of the fact that it's fed on task A data, right? To be potentially better at task B. Okay, so now you want to take this thing and tune it for task B. Take everything. So you're going to train this head and this together, right? It's like fine-tuning setup. But you don't want to screw up on task A. Like, you don't want to have the performance suddenly degrade. Ideally, you'd like it that the performance on task A gets better. Right? That would be the best case scenario. right? And if you did the shuffling in together, you'd expect that to happen, right? Because more data is, there's like two things, right? It's specific to a particular distribution in a particular task. That's a down thing for it. But it's also data. And that's a positive thing for it. Okay, so does that help answer your question? Okay. So suppose you only have task B-specific data. What can you do? Yeah.
Data of task B to through task A and generate its labels, and afterwards use it as a new data set.
Exactly. Great idea. So the thing is, so I'll repeat this. The thing is, you say, what am I missing? Right? I'm missing task A labels. Right? So if I had task A labels on task B specific data, then I'd be fine. At least I would still have to deal with the fact that my distributions have shifted. And I might get catastrophic forgetting from a distribution shift. But at least I have labels that I can use to apply pressure. So now the question is, how do I get those labels? You look around, you say, what do you have? You have a task A head. So you can ask the task A head to generate labels. Okay? So this is called, the idea, underlying idea here is called knowledge distillation. The idea here is use a neural net to generate, augment, labels, and use that to train. It's a new network. So here, what you're going to do is, so the recipe, for example, would be use numbers. Generate pseudo labels for task A on task B data by using so you have the model when you started was good at task A. So just take all of your task B specific XIs and run them through the model. And you will get task A pseudo labels. So now the question comes down to interpretation of how should I interpret these labels? So if you think about task A as being a classification task, understand the details. How do you make a classification task work? You make classification task work by having some network, top of which is a linear layer. The linear layer will generate scores for the different classes, right? Then you'll take those scores and you run through an argmax to actually do something at test time. Everyone remember? So when I generate the pseudo labels, what you're going to generate is actually those scores, right? Because you don't actually trust the argmax to be meaningful. And you're throwing away a lot of information that is potentially captured in this network by just taking the argmax of the label. Okay? But the scores are carrying real valued information which can be useful for you. So these pseudo labels are generally vectors. They're vector valued. Even though many tasks, your labels are not vector valued. Okay? So then what you do next is to use the relevant or a relevant knowledge distillation loss. On task A pseudo labels, during task B fine tuning. So what do I mean by this? Okay, so because these pseudo labels are vectors, you have more flexibility in choosing this loss. So for example, when you think about standard cross entropy loss, right? Your standard cross entropy loss says, I'm going to take the label that you were given, and you're going to treat the label you were given as though it was a one-hot probability, right? 100% probability of something, 0% probability of the other labels, right? And standard, cross entropy loss, well, then takes that and then, does a softmax on scores and says, I'm going to use the softmax on the scores, and I'm going to do a probability, a KL type loss with this one hot, okay? But here, your pseudo labels are these vectors of scores that you've collected. So you have a choice of what to do with those scores. One choice could just be take those vectors of scores and turn them using softmax. Example, turn scores pseudo label into probabilities using softmax and use cross entropy. So that says the labels here, you're going to turn them into probabilities so you have actually more fine information. Now, why is that? Because in many cases, if there was a distribution shift, a significant distribution shift between task A and task B distributions, suppose that task A is classifying natural scenes, right? Outdoor scenes. Are there mountains? Is it winter? Things like this. And task B is like medical images, right? So if you ask the task A thing on a medical image, is this winter, right? Or is it summer or spring? Are there mountains? It'll be like, okay, right? You don't expect the numbers that come out to be, oh yeah, it's definitely winter. Do you see that? Like, it's sort of meaningless. So that's why you want to use both the scores and a knowledge distillation loss to make sure, because what do you care about? What you care about is, please don't collapse distinctions that are relevant for task A in your fine-tuning. Like, don't lose distinctions that are important. Those distinctions will presumably be reflected in variations in those labels, in those pseudo-labels, in those scores. So you want to make sure you keep that variation. You see that? So one way is to do this. There are other ways. So in many cases, people have found that turning these pseudo-labels into probabilities using softmax doesn't work as well. That instead you want to use some of these like polynomial type approaches. So another example. So instead of softmax, you can use things like this. So the ith category, you have a score. I'll call it hat for the estimated label. You take it and you take the tth root. T is just some hyperparameter. And then you normalize by sum over j. All those scores taken to the tth root. Okay? So you do something like this to get the probabilities. What this does is, this is softmax. Remember, softmax is something where you're taking advantage of the fact that the exps and the logs together are basically strongly rewarding the winner. This also rewards winners, but not as much, because you don't trust them as much. It's kind of the opposite. Now you can adjust these parameters of what this t is. I mean, you could also have fractional t, which would be raising it to a power. Yeah.
And so, can you use basically like a similarity score between tasks to tune that parameter? Like, does the similarity of the tasks then affect that process?
Great question. So repeating for the recording. The question was, the choice of this hyperparameter and the choice of the relevant knowledge distillation loss in general, is this affected by the similarity between the two tasks? And the answer is yes, right? And then the question was, can you use techniques that look at the two tasks and tries to figure out what might be a good guess for those parameters? And the answer is, again, yes. The problem is one of context, right? So that's more an engineering approach, where you say that, okay, you don't actually, this is like saying if I didn't have access to task A data at all, to understand the similarity between two tasks, you presumably have to look at examples of the two tasks in some way, right? And then use that to measure similarity. So that people have played around with this, of how you might do that. But yeah, it's, there's no like a definitive answer how to do it. So an example for a hyperparameter here, t is like 2 for the square root. Okay, like just take a square root. Okay, yeah.
So going back to the beginning, how do we even know if like task A and task B is similar? Like, when should we use the pre-trained model for the task A to train the task B?
That's a great question. So the question is, everything I'm saying is predicated on the idea that I have a model which is pre-trained. It has been fine-tuned on task A, and I should be using this model to also deal with task B. But how do I know how to make that choice? Right now, the answer to that question is judgment. Okay? But remember, if you're doing this in an online fashion and you have compute, okay? If you have compute and you're doing things in an online fashion, then you always should ask the following question. I have to choose between this and this. Why not do both? Okay? Do you see that? I have compute. I'll do both. But there's still the question of, what answer do I give? Everyone get this? If I'm going to do something and I say I'm going to do both, I still have to give an answer. How do I give an answer? So it depends on the context. Now you have another set of techniques you can bring to bear, right? First choice is you could just use it, treat it as a hyperparameter, right? This or this. Do both. Now use held out validation data to make the choice, right? That's one way of doing it. But if you're doing this and you're saying, wait, everything here, this new, old, everything is like more sequential, an online process, right? How do I do hyperparameter like choices in an online fashion? And the answer is, why not do that? I use mixture of experts, multiplicative weights, bandit-style algorithms to make choices between both. Okay? So there's other techniques that you can bring to bear to help answer that question. Yeah, again, sad. We don't talk about the bandit and multiplicative weights and that stuff in 189. So I think sometimes it gets covered at Berkeley in 170. Yeah, but not bandits. Not the bandit style, yeah. So, but yeah, we try to fit stuff in the curriculum wherever we can. It's good to know that for the practical problems. Okay, everyone cool with understanding how this kind of approach can work? Okay, this is sometimes called, the paper that introduced this was called learning without forgetting. So sometimes called the learning without forgetting approach. There's many other variations that people have. But there's a general engineering principle that you need to be aware of, which is important if you think about the road to ChatGPT. And the engineering principle that knowledge distillation in particular brings out It says, how do you solve a problem? You solve a problem sometimes, you also do it in math, by saying, I know how to solve the problem if I had blah. But I don't have blah. Okay? This step, before you start learning engineering, you think of as being, oh, well, I don't know how to solve the problem. But actually, you now have learned something as a human, as an engineer, as a designer. You say, hey, if I can get blah, I can solve my problem. So the deep learning strategy here, general strategy is, so how do I get blah? I look around to see, can I train a net to do blah? Or do I have a net sitting around to do blah? If the answer is yes, great, now I have blah. And I can solve my problem. It's the same pattern that you learned in the context of math, right? Where you say, how do you prove something? Well, if I knew this, I could prove it. Well, look around. Do you have a lemma or something that gives you this? Okay? You saw this when you learned how to program with the whole idea of functions and abstraction, right? You say, decompose your problem, then write functions for the different things. So that same idea you want, as an engineering principle, you want to bring to deep learning. It's actually a really important thing about this moment in time is that we're making the transition to doing that a lot more in deep learning than we used to. We used to often just solve the problems end to end for the problem we have starting. And now we're taking more of this approach, which is common to everything else that we do. Okay, yeah, successfully as humans. Yeah, you know, like a part of this is also the idea that we're not going to be able to get to, but it's related, is the idea that human beings don't just use tools. Human beings use tools to make tools. And this is really important. Human beings for hundreds of thousands of years just used tools. But when human beings figured out you can use tools to make tools, right, that made a difference, right? And then things start accelerating much, much faster, okay? So, talking a little bit more about knowledge distillation. Let me step back. Kind of philosophically, it's important to understand, like, this felt like maybe, it might have felt like this is like magic, what just happened. Okay, so let's try to understand it stepping back philosophically a little bit. And then I want to get to meta learning. Okay, so So there's a philosophical question at the heart of this, okay, that engages with this question. So let me pose that question to you. I'm going to give you a set of data points. Okay? They're data points. I drew them. Okay? They came from some experiment conducted in the real world. Okay? Now, I'm going to fit a line to them. Okay? So this line was fit. There's two things. There's the line, and there's the data point. Philosophical question is, which of these is more real? Okay? Do you understand the question? Okay? Kind of it's at a human level. It's like, what's more real? The line or the data points? And the answer to this question is something that you can actually like think about and kind of can see both sides, hopefully, right? The argument for why the data points are more real is because they came from the real world. They're closer to nature that you measured. But the argument for the line being more real is that the line has smoothed out variation which might just be from your experimental apparatus. You're trying to understand something about underlying nature. You built an apparatus, the apparatus was noisy, and so you got these data points, and the line kind of gets to smooth out what's happening and might be a more faithful representation of the actual underlying pattern. So it depends on your perspective of what do you want. Does everyone see that? Yeah.
So is that kind of like the intuition of like Plato's forms a little bit, where like there is some actual perfect sense of reality somewhere?
Yes. So this is related, of course, to Platonic, thousands of years old, right? Every culture has kind of engaged with this problem. And the underlying thing is that, for example, in Plato's perspective says that the real world that we observe is a reflection of an underlying, more pure, ideal reality, which actually exists. And we see things that are kind of projections of that world into our mortal existence. And so from that perspective, the line is trying to get at a representation, a mental representation of the thing in the ideal world, right? And the points are like the shadows, right, that we experience in this world. And so, yes, it's related to that. But this is also like the heart of what we're doing in machine learning all the time, right? In machine learning, we're trying to learn how to generalize, to learn the underlying pattern. And so the idea in knowledge distillation is to say, when you don't have data, maybe you have something like the line. Okay? So suppose that I didn't have data here. No data. Okay? But I do have the line. If I needed to have data here, where I have none, what can I do? Well, I can say I need data here. Let me just evaluate points on the line as my data. And maybe I can regularize a little bit, because I don't trust it, because I don't actually have data there. How can I regularize? Well, I can do it in many different ways, which you learned in this class, right? You can do it, for example, by adding noise to it. Right? You had homework where you did this. So this is the idea of knowledge distillation. Its knowledge distillation says, treat a trained neural net like the line. And use it, query it, to get data when you don't have data. So, does everyone understand the idea? It's not a very complicated idea. It's a very basic idea, right? And it's related to this more foundational idea that you see in math and everywhere else. It's like, let's treat instead of treating the neural net as an end product, treat it as a function. And feel free to call it as you need to during your process of training. So where is knowledge distillation used? It's used in lots of examples. Lots of context. It was originally developed in the context of saying, suppose you trained a big network, and the big network learned something, but you need to fit it into a smaller device that can't hold the big network. So you can use knowledge distillation to treat the big network. So the big network learned. You hope that something reasonable will fit in the smaller form factor. Okay, so hope. But if you just trained on the data that was successful to learn the big network, it doesn't train to the right thing. Like, it doesn't work well because the network is small. So you think, maybe if I had a ton more data, I could train it. Right? Or better data, I could train it. So you look at this and you say, hey, knowledge distillation, this line. All this stuff, the spread of these points, if that's actually coming from noise, imperfection, not something in reality, then that's noise that's being injected into my training data. Classic machine learning perspective of bias variance trade-off in under-parameterized models tells you that stuff is going to shake your model. If you could get cleaner data, for example, from the line, you could learn better. Okay? And you could also potentially get more data. So all of that is used in the context of knowledge distillation for getting a big model or an approximation of a big model to fit in a small space. People have also played around with using knowledge distillation itself as a way to train a single model better. And so sometimes it's called, so use cases aside, 1, make a smaller model leveraging a big one. And another case is just to improve the training of models. So this is sometimes called self-distillation. So self-distillation idea is you train a model. That model gives you a counterpart of a line. Then you use that model to train another model of the same size, using a combination of actual data and stuff you get from the model before. So kind of repeat. And see if that will get you better and better models. So this actually does work in practice in many cases to get better models. So knowledge distillation is a very important idea to keep in mind. It's, so I want to make sure you knew it. OK, so at this point, we've kind of built a lot of the things, at least on the road to ChatGPT. Like you have a lot of I've introduced some ideas. What I want to do now, though, is actually change gears a little bit. So first, are there any questions on what I've talked about?
Yeah, so how do you generate this line if you don't have the input data, for example, for task A?
Great question. So for task A, in the example we're talking about of learning without forgetting, catastrophic forgetting, so we did this, right? So we generate pseudo-labels for task A. So we have the line. And we have where to evaluate it from task B. Task B told you where I'd want to know where task A was evaluated.
So what if you have very different tasks as
You exemplify it earlier.
Yeah. So the question was, what if you have very different tasks? If you have very different tasks in the sense of what their input data distribution looks like, when you do this knowledge distillation idea of querying, like the example I gave, you're querying a model that classifies natural scenes on medical data, you're asking that model, in effect, to extrapolate. Okay? So generally, when you ask models to extrapolate, what comes out might be total gibberish. Right? You just can't trust what comes out. But when you say what comes out is total gibberish, you have to say, what do we mean by total gibberish? What do we mean by total gibberish? What we mean is that it's no longer physically relevant in terms of the underlying task. But in the context that I just told you about task A is a natural scene classifier, and task B is medical images diagnosing cancer. If you ask, given a medical image, what was the weather? The answer is gibberish, but that's fine because the question is gibberish. Do you see that? Like, the question has no meaningful answer. So in cases when the question is meaningless, the fact the answer is meaningless might not be a problem. Right? You see what I'm saying? The bad things about extrapolation might not be bad for us in that context. I mean, you still have to worry, right? Because what we're going to count on it to do is to make sure that we don't perturb aspects. We're trying to use the idea of make sure we don't perturb distinctions that this thing is making that are relevant for task A. And so even if the way that those distinctions get processed up through task A is such that the results are meaningless, the fact that those distinctions are there might still be present. Of course, there's still a danger. There's still a huge danger. The huge danger is that the data for task B is such that it does not even excite the modes here, right, that are relevant for task A. Like, that variation isn't excited at all. In which case, a collapse along those modes that are happening here would not be stoppable with this approach. Okay? So the fact that it's hopefully exciting the same modes is like a leap of faith. Does that answer your question?
Yeah, so you have to be careful about how you design this knowledge distillation loss then, such that you guarantee some kind of similarity measure.
Okay, so you're asking the question of can we combat this by the choice of knowledge distillation loss? And the answer is not really. At some level, there's going to be cases where the richness of task B data itself is such that that's the limitation we have. No knowledge distillation strategy will be able to give us observability on the thing we're worried about in what was originally the pre-trained or the shared parts of the model. Right? The choice of the loss won't fix it. Now, there are cases where you do have some degree of observability of that thing, in which case the choice of the knowledge distillation loss has to make sure that the force of the gradients is strong enough to stop collapses there. Okay? In that case, it does matter. But it's kind of there's no like perfect knowledge distillation loss that will solve the problem. It might be impossible. But we accept that. Okay, good. Any other questions on the stuff covered so far? Okay, I'm like slow. So I want to now talk a little bit about meta-learning, which is important. So the perspective that meta-learning takes is that the important thing is fine-tuning. So it says that what you want from your model, it changes the perspective from what you want from your model is good performance on a specific task to what you want from your model is that you can fine-tune it well to tasks that you see. Do you see this? Right? It changes the goal. So you want a model that can, the reason it's called meta-learning is you want a model that has learned how to learn. We think of fine-tuning as being learning. Okay? So this is learning. So want to learn how to learn. So that's why it's called meta-learning. But to demystify it, I'll say So want to learn how to learn is we want to be trained so that we are good at being fine-tunable, right? Which is the practical consequence that you want. So in a model that I can fine-tune well. So the fact that this was important became clear to people the instant you started, even with ImageNet, you started using ImageNet, models trained on ImageNet, to be then fine-tuned for other tasks. People already saw that. The approach we've talked about so far with self-supervision is, look, let's find a proxy task. Let's hope the proxy task will help us learn something that we can then fine-tune. The meta-learning perspective says, wait, we know what we want to do. Because we know what we want to do, maybe we can be good at what exactly we want to do, as opposed to simply hoping that we're good at it. Does everyone see the distinction? One is you treat fine-tunability as an interesting emergent property that happens after you've seen enough data and had a rich enough task that you trained on. And the other says, look, if I know I'm going to have to fine-tune in practice, maybe I can take that into consideration as I actually train my model. Okay, it's important to understand the distinction here. So the question that we want to answer, right, is how can we do this? So this is actually interesting, approaches. And a part of it is your approaches are going to be determined in part by what do you have access to. Like what's kind of data? You can only train when you have some kind of data. The kind of data that you have determines what you can train, how you can train. Does everyone see that? Like, so if we want to begin to answer the question of how do we get good at this, we have to presuppose something about the data that we have. And so I'm going to describe, so I'm going to assume that I have data on multiple tasks. At training time. Okay, so I'm going to have tasks right, and I'll have data sets. Xij, Yij, where this is ith task, jth sample. Suppose I have a data set of data sets. Did everyone see this? I have a data set of data sets. And I want to use the data set of data sets to do what? Right? I want to be able to generalize. What do I want to generalize? Machine learning is all about generalization. Generalizing, I want to generalize being fine-tunable. Right? So I would like it so that goal given a new task. What's a task? So x test j, y test j, right? I do well on it. And what does doing well on it mean? Right? It means I will do well on held out data. Test, test. Do you see that? Like I'm just going to operationalize what it means. So I have a data set of data sets, and I want to do well on a new task, which will be a new data set. And doing well on it means fine-tuning on this data and doing well on held-out data. Is the problem setup clear to everybody? Yeah?
Do you care about like forgetting the initial tasks at all?
Good question. So a good question is, do we care about not forgetting these initial tasks? It depends, right? It depends. Here, I'm just going to, the standard perspective that people take, initial perspective, is just that all I care about is that I be fine-tunable on the new task. I don't care if that fine-tuning causes some problems elsewhere. I just want to be fine-tunable here. OK. But it's really important to understand that there is an intellectual, very significant intellectual connection between forgetting and learning fast. OK? What is this really important connection between forgetting and learning fast? So usually when people are thinking about this, the goal is that you should be able to learn this new task with a little bit of data. So this problem really came to the foreground in the context of both practical problems in the real world, where you have a situation where things are changing rapidly, and you want to make sure your model doesn't take forever to catch up, okay? In many, many situations, as well as problems in the context of robotics and other things like that, where training data is really expensive to get. So you don't want to use a lot of it. You want to use as little as possible. So it's kind of sitting in the background. So the first thing to understand is, what is the connection between forgetting and fine-tuning? Okay? Here, it's helpful to think about it in the context of when you have only a little bit of data. Okay? Why is having a little bit of data helpful for helping you understand what's going on? So focus, intuition. For a task. Why is it helpful? It's helpful because when you only have a little bit of data, what that means is you have less data than the size of your model. Okay, your model is big. We started off the course talking about this, right? Your model is big. Your data is little. So why is there any hope that you would be able to learn the task? The reason is you think that the model that you have and the initialization you're dealing with is such that there's only a few important directions. When you look at the linearized model around your data points, and you look at the SVD, that you expect for that linearized model that there's only a few directions that have big singular values, and the rest of them have small singular values. And you hope also that whatever pattern it is that you want to get is actually representable by the singular vectors that correspond to those big singular values. Because that's all gradient descent is ever going to learn. Right? Remember, we talked about this multiple times. So what you're thinking about is that when you have a little bit of data, right, this means what matters is the locally linearized model around training data. And all you can do when you're fine-tuning the weights is to move along those big singular vectors in such a way that you get a new pattern. But this also tells you why you might forget. Because if those big singular vectors are such that they're actually the same across multiple tasks, then you align them one way for one task. But that means you just misaligned them for the other task. Do you see that? Like the two are related. Now, if it's the case that the neighborhoods of the training data are such that they're very different for the two cases, and your local neighborhoods in both are different and have singular vectors that are very different from each other, then it might be that moving along this one does almost an insignificant perturbation for this one. Because the directions you moved here are largely orthogonal to where the main action is for singular vectors here, so who cares? Okay? But it tells you this is related to if tasks are close to each other, right, is exactly when you expect you might forget. And it's exactly where the approaches we talked about before would help stop you from forgetting. Right? But this approach will only stop you from forgetting if it can, right? If there's actually not enough actual tension between these tasks. Okay, so like this helps you understand the relationship between these different ideas. Okay, so in the very little amount of time I have left, once you think about this stuff this way, there's a very natural strategy you might follow to do well on this. And what's surprising is in the history of this field that crystallizing the fact that this is a question that you have, okay? This is the question that you actually have, and asking what's the baseline approach that you might want to compare to happened relatively recently. So the approach I want to talk about is actually, we can consider that baseline approach, which is called MAML. MAML stands for model agnostic meta-learning. So let's demystify it. Model agnostic means, look, there has to be a strategy that you can think about that's a baseline that doesn't worry about the details of the model. Okay? So model agnostic just means think about the simplest thing, the first thing you should try. Meta-learning is the problem. So the MAML strategy, which we'll talk about more on Monday in more detail, basically says, if this is the problem that you have, why don't you try to solve it the exact way you solve every other problem that you try to solve? What is the exact way you try to solve problems? You say, in the context of deep learning, it says, take SGD steps. So what does SGD steps mean? Draw a random blah. Now, evaluate how well do you do on blah. Compute gradients, update, and repeat. Right? That's the general pattern of SGD. So what MAML says is just that, what is your blah? Your blah is, given a new task, fine-tuned to do well on it. Right? So it says, key idea, I'm just going to do SGD on this. I have a data set of data sets. So I randomly draw a data set. I take my model, and I try to fine-tune it for the problem I have. I see how well I do on a held out set. Then I compute a gradient. A gradient to what? I want to do learning. But what does that mean? I'm learning some weights. The goal, at the end of this, the goal is to give you a pre-trained model. So I do a gradient update on those weights. And then I repeat. It's literally So Chelsea Finn, who's a grad student here, together with Sergey Peter, said, hey, let's try to do the simplest thing first and see how well it works, which in hindsight is way easier than all the things that people thought about before to think about. But just required clarity of thought. So just try that strategy. We'll talk more about that strategy on Monday, to work it out, tell you some of the key challenges that that strategy does. When you think about that strategy, it opens a natural connection to RNNs, a natural connection to other ideas. And then I'll try to bring you up to where the current state of understanding is about using mammal-style approaches versus other approaches. Because there's an alternative that you can already think of. The alternative is just pre-train on this. Have task heads for every single one of these tasks and just pre-train the whole mess together, right? Versus doing this strategy. So we'll talk about that next time. Okay. And then I'll move on to generative stuff, which I do want to make sure we spend enough time on.